So thanks for coming. This is the sort of, let's say, teaser version of a longer talk. So I had to cut something. I had to pick some interesting examples so that I can sort of tease out the idea, engage some dialogue, sort of make you come up to me afterwards, ask me questions, engage, start a conversation. I do have a longer version of this presentation that I will be presenting at another conference this year. So if you're interested, just keep in mind there's way more material. Why symmetry? Why should we bother with symmetry? Why should we care? It's an interesting fact that nature exhibits some sorts of symmetries with regards to objects and phenomena in the universe. And it's even more interesting that the human mind seems to be very fascinated with these kinds of symmetries. We seem to associate symmetry with some kind of perfection or ideal. We tend to be very drawn to asymmetrical things. We have a tendency to investigate symmetrical patterns and identify emerging properties from symmetries. So this has followed humans throughout history, in science, in art, and programming being a creative activity and having a very being very humane in nature. Of course, there's these kinds of concerns penetrate the way we think about code as well, the way we design and organize code, and how we design systems in general. So in general, we tend to pay attention to these kinds of things. They sometimes stick out, even if we're not looking. And we some way instinctively are drawn towards these kind of things, but sometimes they're sort of elusive, and we fail to achieve these kinds of things. So I think it's a very old thing. It sort of goes back to ancient Greeks and their idea of perfection in shapes and phenomena in nature in general, and how they saw matter being composed, how they saw the universe, and the idea of geometric shapes and symmetries in geometry. That was sort of at the core of our scientific endeavor. And they were sort of horrified about this idea that movement of planets are not tied to this perfection of the circle shape, and somehow these trajectories are near perfect. They're sort of like circles, but they're not quite circles. There's just like this dissonance between the ideal representation of geometrical concept and reality. Observation of reality sort of bothered them a lot, and this came up in various other things as well. So there's various kinds of symmetries, and there's interesting properties emerging from all sorts of reflections related to symmetry, and even interesting properties that arise from asymmetrical things in nature. For example, one such thing is chirality, which manifests in chemistry, in biology, in organisms, and in physical phenomena as well. I picked here like three different things. One chemistry compound example, some sea snail, I believe, which are actually two kinds of instances of this kind of snail, which have different kinds of structure for their shell. And of course, the famous example of polarizing light through sugar water, which sort of became famous. So I want to take a sort of look through this kind of lens and analyze how these kinds of things affect coding and how we think about systems in general, sort of through this lens of the physical scientist, through this lens of the observer, the ever in a continuous pursuit of understanding and finding deeper and deeper layers in these kinds of patterns in nature. And just as an example, and how many of you are familiar with character of physical law series? Feynman? No? Just a hand. 2 hands. Okay. By the way, I have almost all slides. I have like tons of links in them. So when I'm gonna share them, just feel free to explore on your own. So from Feynman's character of physical law, a series of lectures from the early 60s, some of these interesting symmetries that I think at least some of them are familiar to all of you. And I think there's an important inflection point in human pursuit of these kinds of symmetries and patterns, where we went beyond examining geometrical patterns, because those were the first attempts. And when we thought about not just observing these patterns, but also what kind of transformations can we do to conserve some kind of invariant or some kind of property about a phenomenon or about an object itself. So in a purely abstract way, by the way, who recognizes this mathematician? Anyone? No? So I'll give you a clue, is a mathematician that died very, very young. I think I heard someone, Évariste Galois. Yeah. Died very young, did a lot of things. Died at 20, but probably did more than many, many other mathematicians. So one wonders what could he have done. So he was the first one to extend the idea of looking at transformations and symmetries beyond geometrical things, looking at algebraic structures, looking at equations, looking at functions, polynomials, number theory, and so on. So that was a big jump in human understanding of these kinds of patterns in nature. I was about to ask who recognizes this physicist, but the name is right there. Okay, so another one of the giants, Murray Gell-Mann. So again, links are there. Very nice presentations, by the way. So another such example is looking at discoveries and emergent properties that came out of just not measuring or experimental observations, rather looking at the theoretical shape and mathematical representation of various phenomena, and discovering emergent properties and laws and even particles just from the beauty of the mathematics and the symmetrical transformations from the mathematical representations of these things. So purely from theoretical standpoint, discovering truths about nature and about the universe. And it's a very interesting story, in particular, with regards to a collaboration that Gell-Mann had with some other physicists, where they came up with a theory that was so beautiful, and it was just a theory. And by the way, when people say theory, they usually mean like, oh, conspiracy theory, like theory of whatever. It sort of got this like lightweight, watered down meaning. When I say theory, I mean scientific theory, right? With proofs and mathematical foundation. So they got these ideas, and they found this beautiful math to represent and model the weak force. And when they published, they were so sort of mesmerized and happy about the beauty of the mathematical representation of these things, that they completely ignored that their theory was in contradiction with 7 experiments at the time. So they published it anyway and said that, oh, probably the experiments are wrong. And they were right. All 7 experiments were wrong. So the theory was so beautiful that they were convinced they were on the right track, and then later on they were proven right. So there's the elegance of these layers, as Murray Gell-Mann calls them, like the onion layers of getting to deeper and more distilled forms of the truth. They lead you to inherent truth and inherent realities in nature. Sort of nature is conformant to itself. Sort of these kinds of pursuits in symmetry and beauty in representation, and especially through mathematics, which is the perfect language to model reality, gets you to the actual fundamental truths, gets you to the better theory, the better representation, the more accurate form of it, or the more succinct way, or the way in which you can extend it to other things. Just a quick example here for Maxwell's equations for electricity and magnetism, for example. The original representation that Maxwell did clearly exhibits symmetries with regards to rotations in space. So you don't have to understand what's going on there, just appreciate how it looks. So, but you can clearly see some patterns there. There's some X's and some Y's and some Z's. So if you squint, you can probably figure out that these laws are independent of how you rotate space about all three axes, right? So there's rotational symmetry. But it's definitely in the original Maxwell form, they're very verbose. And applying later on, other physicists applying rotational symmetries and vector analysis and some more clever maths and symbols there, they managed to distill those and convey the symmetry through higher vector symbols and mathematical constructs. And later on, exploiting totally different kind of symmetry, not 3D symmetry, but symmetry related to special relativity, Einstein distilled them, the very same equations, even in a more simpler form, which just say that all electricity and magnetism comes from charges and currents. And there's no other magnetism other from than those coming from those. Okay, so going back to our activity and programming and how we structure code and how we devise systems, there's all sorts of very rigorous, in the same fashion that physics is, very rigorous ways of quantifying code and analyzing topologies and figuring out conditions, proving invariance about code, associating all sorts of metrics with regards to code. A very good presentation, I think. Just there's a bunch of series of presentations from Lisa Lippincott in this vein. So I'm not going in that direction. So that's very valuable for people who are interested, and I put a link to maybe I would say the starter one in the series. So there is enormous benefits in being able to prove facts about code, about your functions, about structure programming, about how you loop through computation and so on. But I'm not concerned with these kinds of symmetries and patterns. Again, link to Lisa Lippincott's presentation if you're interested. I'm much more interested in shapes, as in how we structure, and if we manage to change these shapes, what can we do, or what these shapes can tell us about program and opportunities of improvement or potential problems with it, right? Like this, I think we all recognize this kind of shape in our code. We recognize this kind of shape in our code, right? Sort of paragraphs, right? Opportunities here being like maybe these kind of blocks, these kind of paragraphs could be independent functions, so opportunities for refactoring, for providing a name for those blocks. Even better, looks like someone tried to help us to refactor. They put some comments there, so maybe we can transform those comments into some meaningful function names. So again, these kinds of structures point us to the kinds of things that we might try to pursue to improve the code. improve its understanding, improve its extensibility. Again, I think nothing is unfamiliar here. These kinds of unbalanced branches, either if or else. Uh, more on these just a bit later. And again, I mentioned these kinds of, applying these kinds of metrics, and there's even formal mechanism through which we can infer transformations that we can apply to the structure of the code. But I think if nothing else, if you get nothing else from this presentation, is just follow that link and watch this lightning talk from James McNeilis. So it's by far the funniest lightning talk I've ever seen at a conference about the shape of a program. Just a few things there. It's about, it's funny but serious. So a way of quantifying complexity by sort of the area under the code there, sort of. The more indented it is, the worse it is, right? That would be the insight from James in that presentation. And it's super funny, but it's also true. So, and there's various ways that we can tackle with this kind of thing, the sort of flattening using guards and early returns. This sort of thing, we're used to seeing these kinds of things, right? I even, so that I'm not accused that I show only C++ stuff, I have here, there's languages that have specific patterns in the language syntax for these kind of things. For example, in Rust, instead of the if-let structure that leads to these kinds of indentation, where the interesting bit is actually right there nested, there's special syntax, this let-else syntax that allows you to do these guard statements for early return. In Swift, there's a very similar thing. Again, they even call it guard, right? So very, very suggestive. So it allows you to sort of invert the shape, the structure, so that you get a more easily readable and extensible code. So, and going beyond the shape and maintainability and how you massage the code into a form that it's better for you for the future. In general, left-leaning code is not just about, oh, I hate looking at it like that, so indented. Left-leaning code generally tends to be faster because it means less if, less nesting, less branching, right? So again, I picked just one example. If you look at this presentation, and I strongly encourage it if you do, in case you didn't see it. So performance is in the minds of people. There's a thing that I highlighted there, size and one. You see that thing there? Definitely doesn't look like it belongs in that expression where it calculates an index range, a bound, right? Why would size and one be there, right? So it tries to figure out if the size of the array is odd or even, right? That's the obvious part. But why not stick an if size and one, right? And then move the position, the pointer to the right, sort of to position the computation, the loop in the right position, is to avoid that branching, right? And the clever bit here is encoding the conditional in the arithmetic operation, because you don't pay the cost of branching. You've put that decision inside how you compute the index, and then you don't pay the penalty of branching in the CPU for that. So these kinds of things, these kinds of patterns that take you to lean left in your code will give you even better performance, right? And in general, we have to think about these kind of incidental versus deliberate symmetries. Like, did we mean to omit giving the symmetrical operation, or do we want to allow the opposite? So we allow adding. Do we want to disallow removing? Are we adding it just because it's symmetrical, and are we expected to have it, or do we really need it? Do we need to have this operation? Be explicit about it. Don't add it just because oh, I have the other one, so I might as well have this one, right? We have to be very deliberate. If we don't want an operation, be very deliberate that we omitted it on purpose, not just, oh, I forgot to implement that thing in the interface, right? So be very deliberate in disallowing or not publishing operations. So in general, we should be looking to identify these kinds of patterns and see if they yield some benefits. They don't always do. For reliability, maintenance, performance, discoverability, and so on. And I'm out of time. This is the takeaway from the talk. Thank you.